implementation of each and every unit using logic gates, but we now understand at least that how the block level architecture looks like. Okay. Now, since the instructions will be passed through this architecture, we must now understand that how the hardware can be designed. Okay, the gate level hardware designing. But before we know that how gate level hardware can be designed, we should focus a bit on understanding that how the instructions are represented, or in other words, we can say that encoding of the instructions. Okay. Even though I have mentioned this encoding time to time while discussing the architecture in previous classes, but let us now formalize the instruction encoding. Okay. So we know that instructions are kept in the computer as a series of high and low electronic signals. Okay. So it's basically a binary signals. In fact, each piece of an instruction can be considered as an individual number. So you represent this number in any number system, in decimal, hexadecimal, binary, depending on what is your convenience. But the hardware only understands the binary representations, that too in the form of voltages, 0 and 1. So since registers are referred to by almost all instructions, there must be a convention to map register names into numbers. Okay. So what we will take for instruction encoding is MIPS 32 architecture. Which is obviously a RISC type architecture. So it has a total of 32 registers, and their names are given separately depending on their utilization. So in MIPS, registers are named using $. Okay. And so they start with $ symbol and followed by some other symbols also. So for example, $S0 to $S7, this actually map into register numbers 16 to 32. Sorry, 16 to 23. 16 to 23. Similarly, registers $T0 to $T7 they map onto register 8 to 15. So it means whenever you mention $S0 in any instruction, you mean register number 16. Okay. When you mention $S1, you mean register number 17, and so on and so forth. When you mention $T0, it means register number 8. Okay. So you can see that here basically 8 registers and 8 registers, 16 registers we are already discussing, remaining 16 we will talk later stage. Okay. So there are general purpose registers. So some of these are used as general purpose registers. There are more temporary registers. Okay, we'll look into map. So this is a convention, just giving a dollar, while in your instruction, assembly instructions, you write a dollar symbol. If you look into the examples that I have discussed in the class, I have never used these notations, but these are just for assembler to understand that what is the register number. That's why. Okay. This is just a convention. There is nothing that we need to follow exactly the same thing. Okay. Now assume that we somehow mapped this registers. So this is a mapping of registers. Done. So the mapping is obviously from 0 to 31. Mapping is for 0 to 31. So 0 to 31. So you know that the values in binary, so this is obviously decimal, the values in binary will be 0, 0, 0, 0, 0, 2, 1, 1, 1, 1, 1. So this is in binary. If you now take an example, any instruction, let's take add $T0, $S1, $S2. Let's say this is an example instruction. We're talking about this an example instruction, and it's binary, its decimal representation for all the fields may be something different. Okay. So since it is a 32-bit architecture, it's a 32-bit. The whole instruction will be encoded within this 32-bit. And MIPS uses 6 bits for opcode. Six bits. 1, 2, 3, 4, 5, 6. Okay. And depending on the value of this opcode, remaining fields are later on defined. But they are also divided like this. Here you get 5 bits. Here you get 5 bits. Just a minute. So these are all 5 bits blocks. I have not defined again what are these blocks. We shall look into latter stage. So 20 plus 6, 26 plus 6. 6, 5, 5, 5, 5. And opcode is obviously 5. Now this field is fixed. Even these 3 fields are also fixed. Okay.
Opcode is 6.
Oh, code is 6. Sorry. So total is we have 32-bit.
The first opcode is fixed and
Opcode is fixed. These are also fixed, but sometimes they may be combined. So they are block wise 5, 5, 5, 5, 16. So I can have now options like 6 plus 26, another option. We can have 6 plus 5 plus 5 plus 5 plus 11. We can have 6 plus 5 plus 5 plus 16. There are many such variations. So these are very common, common variations. 6 plus 26, 6 plus 5 plus 5 plus 5 plus 11. So when it is 11, you know that these two will be combined. 6 plus 5 plus 5 plus 16, you know that 6 plus 5 plus 5 plus these 3 will be combined to get a 16. Okay. So there may be some other combinations also, but these are very, common combinations. We shall look into this, what these combinations mean actually. So now the fields actually they have some meaning, these fields. Let us now look into these fields. I mean to say that they have given some names. These fields are given names. So names of the fields. This is opcode field. In short, it is written opcode. What it tells? The basic operation of the instruction. This is basic operation. So examples like add, move, jump or branch. These names are encoded using these 6 bits. They're called opcode. So this field denotes the operation and format of an instruction. So this field, depending on this field, the remaining fields are actually defined accordingly. Then the second one is five bits. It's called RS. This is the first register source operand. Source operand. It means if your instruction is add, something like this. Okay, assuming that in MIPS encode, assembly, this is the destination. This is source 1. This is source 2. You know that this field actually contains S2, $S2. This is the first register source operand. The second one is RT. This is again 5 bits. The second register source. In this case, here it is S2, $S3, source 2. The next field is RD. Again 5 bits. This is the register destination. Operand, where the result will be stored. The next field is basically a special field which I have not discussed yet. It's basically a shift and it is called SHAMT, which is 5 bits. It's called shift amount. It will be used in logical operations. Because there is an instruction called shift. Okay, here. So that shift requires how much amount of shifting is needed. So that's why this is a special field. So this will be activated only when this opcode is shift. We will discuss it later on. Shift amount. Okay. This is for shift opcode. Then the fifth, the last one is, the sixth one is the function. Now this field is again 6 bits. So the function field. So the field often called as function code, it selects the specific variant of the operation. So this field helps to select a specific variant of the operation. Like sometimes you need to do, say, unsigned operation, signed operation. There are many, particularly for arithmetic operations, you require various kinds of variations. Okay, so those variations are handled using this opcode, function field. Even you are adding, you would like to apply 2's complement addition, 1's complement addition, or subtraction, multiplication. All these things are actually handled through additional fields which are given in the function field. Okay, so you can say that this operation field is actually taking help of this function field whenever needed, depending on what type of opcode it is. Obviously for move you may not require, but for arithmetic operations like add, multiplication, subtraction, division, logical operations, you need to take the help of these function fields to define different types of operations also. Addition can be done in many ways. Multiplication can be done, signed multiplication, unsigned multiplication, division, you need to take care of several things like borrow, carry, all these things. So everything will be handled through the special bits provided in the function. Okay. So this is the typical encoding of the MIPS 32-bit instruction format. Now let us try to understand one by one different type of instructions that we may deal with. Okay. So various formats of MIPS instructions. See, remember, whatever we are designing in the lab or the 5-stage pipeline, they may not be exactly same MIPS, but this is a real machine. That's why I am giving minute details. Okay, whatever we are doing in the actual design part, I already told you, we are not going to implement any commercial processor. We are going to understand the design concept for a typical RISC processor, but this is a commercial processor, MIPS 32. Okay, so that's why it's better to understand that what that commercial processor actually has implemented. Vis-a-vis, we are already learning the design principles. Okay, so we shall now look into the different formats. There are art type, then we have immediate type. These are primary format. There is another also format, jump type branch format. We'll look into that stage. So basically we can write it is J type, but we shall discuss it later stage. Now let us first look into this one and this one. R type, I type and J type. R type stands for register type, I type stands for immediate type, J type stands for jump or branch type. Okay. Let us first talk about the I type, immediate type. So we will now initiate with I type. So in I type, there is an immediate field. So the instruction is formatted like this. We have opcode, 6 bits, RS, 5 bits, RT, 5 bits, and then there is a constant or address, which is obviously 16 bits. So the 16-bit address means a load word instruction can load any word within a region of plus minus 2 to the power 15. So the base register, within the range of plus minus 2 to the power 15, that means around 32,000 bytes shifting from the base register, okay, RS, which is basically the base register RS is given. So let's take an example. If we talk about load word, the instruction is actually load word. In MIPS, it is load word. When we write like load word $T0, say 32, then $S3. $S3. So what we can understand here, more than 32 registers would be difficult in this format, because as the RS and RT fields would each need another bit, making it harder to fit everything in one word. One word means 4 bytes. One word means 4 bytes. Okay. It's a 32-bit architecture, so one word means 4 bytes. And your instruction is already 32 bits. And you have already reserved 16 bits for constant, 6 bits for opcode. So you cannot allocate more than 5 bits for source register and another 5 bit for another source register or destination register, whatever you call it. So what this instruction does, it does nothing but register $T0 gets an array, gets an array A. Let's assume that A is the base address which is stored into register S3. Okay. 8. So this is the base address of the array A. This is a 16-bit offset. This is a 16-bit offset. So remember, these are bytes. That 32 bytes from the current location. So you know that an integer takes 4 bytes to store. Hello, someone is speaking? Is there anyone speaking? So you know that every integer takes 4 bytes. So that's why this 32 byte offset from the base. It means the 8th element. So that's why, and $T0 is this is the destination register. So don't go by these RS and RST. Here I'm saying that this is the destination register. Okay. Where it is $T0. So the $T0 gets the integer which is stored in memory location A8. A is the base address. The base is stored into the base register S3, and 8th element of the array, because the memory is byte organized and we are accessing an integer value which is stored in one word, and one word means 4 bytes. So that's why this 32 bytes means the 8th element of the array. Very simple. Okay. So this is the immediate format for load. Similarly, we can actually do something for a store also. So store word, you can always write something like the store word, and take any example. You know, complete this field. You can have $T0, say 32, then $S3. What will happen? The register $T0 is copied into A8 location. It seems that as if you are always using an array operations. It's not like that. If you declare, so now look into the point of view the how operating system handles. Basically, where the variables are stored into the memory, they are starting from an address location, and that can be the base address of the variable section, integer variable section. Okay, in the process control block. So where you define those variables, and if it is integer, you know that it will take 4 bytes. So the next integer will be stored from the 5th location onwards. This way it continues. So there is nothing to be worried that whether I am always trying to access an array limit or not. It depends on how do you initialize the base address. Okay. Is that clear? How these two instructions are encoded? So forget about the letters I have used it as an RT. You know that in case of load, both will be source. One will be source, one will be destination. In case of store, both will be source. One will be used for getting the address, one will be used for getting the value. So don't go by the names RS and RT. Okay. If it is load, one of them will be the destination and one will be used the base address. In case of store, one will be used as the base address and one will be used as the source of the data.
Load also, sir, one will be used as an address, right?
In load also, one will be used as address, no? In load and store, one of them will be used as the address, base address. Okay. And in load and store, one of them will be used as the base address. In case of load, one of them will be used as the destination register. In case of store, this will be used as the source register.
In store, T0 is the source. In store, T0 is the source.
In store, T0 is the source. Yeah, because the register $T0 is copied into a location, so this is also source. This is the source of the data. This is the source
Sir,
of the
can you
address.
please repeat? My network went off, sir.
What I'm saying that in case of store word, this T0 is the source of the data and this S0 is the source of the address, the base address. This is the offset, 32 is the offset. Whereas in case of load, this is the destination and this is the source of the address.
Yes, sir.
So another example of immediate type. Let's take another example. Add. Usually given number like this to say that this is an operand. So what it does? It does plus 200. Now you know that What will be the size of the immediate field in case of add? This is 6 bit, this is 5 bits, this is 5 bits. Okay, so you can have, when it is add immediate, you can have 16-bit offset, 16-bit immediate value. So you know that how much will be the constant, how large will be the constant. So if I write something like that, A300 equals to H plus A300. This is a high level instruction. Assuming that $T1 has the base address of the array A and $S2 holds the value of H. So the corresponding MIPS code can be like why this 1200, you know that this is 300th element, so you need to multiply it by 4, assuming that these are their integer values. Each variable takes 4 bytes to store. So this is high level language translated to machine language, and now you know the code, you can actually translate it into the machine code also. That is basically assembler does. But if you would like to do it manually, you can also do it subject to the condition that you know that the values of what are the codes for LW, add, this, and what are the binary representations of these registers. You can also convert it. But this is more or less like a table lookup thing. So assembler can do it easily. So what actually compiler does, the compiler works for here to here translation and the assembler works for here to machine code translation. We write the code in this language, okay, and we use the compiler like GCC and other things to convert it into this, and then GCC uses the assembler's help to convert it into machine code, which can then run. Now, where is the part of the operating system here? You carefully look into it. When I am defining these addresses, here I need to take the permission from the operating system that where is my array and what will be the starting address. All these things are defined into process. Probably now you can correlate that why operating system is needed, because compiler doesn't know that what will be the absolute address of the memory from where your program will be executed. Unless you do not know the absolute address, you cannot load the program counter value with that. So that will be provided by the operating system. So operating system will provide, because it is the manager of the entire system. It keeps track of the entire memory available for the program segment, data segment, code segment, and it provides the base address for those segments. So now you can probably understand that how complex the system is actually. It is easy for us to convert this one to this one, but when you map it to the primary memory, it is really difficult, because you cannot fix it also. Because tomorrow the same program, you write a program, you save it into hard disk. Tomorrow you open the program, compile it, run it, or even compiled it already, you store the binary code into your hard disk. Tomorrow you load the binary code and simply run it, how it runs. That means while running, these adjustments are happening. All the addresses generated, they are relative addresses. They are never absolute addresses. They will become absolute address only after the operating system takes the control. Because as a program, you don't have access or to load your, as a programmer, you don't have access to load your program from a specific location. You do not have the permission. The reason is simple. Because operating system is also loaded. If you try to load your program into the area of the operating system, the entire system will crash. That's why there's a lot of protection given. I think all these things will be discussed in your operating system course, I believe. So, but we need to know that how things actually happen. I'll stop the discussion here. I will take some questions from you now. Let us openly discuss it. Up to this point, anyone, any doubt, anything, you can tell me. And whatever I have discussed today, this is up to the midterm syllabus, nothing else. Whatever I have taught up to now is the part of the midterm syllabus. Yes.
Sir, one small doubt. Sir, when load word is there, we are specifying two registers, and there are two registers RS and RT. So
Hmm.
is that mapping is done randomly, or is there any specific mapping done like that?
No, no, it's not randomly, or it's never randomly. It is specific. Okay. I actually do not know that how actually they have done the mapping, but when you design the circuit, you can do the mapping. Okay. You can do a fixed mapping. Okay, that the first one will be the destination or first one will be the source. That mapping you can do it. It's basically connecting these two RA and RB. Yeah, do you agree with me? This one is basically connecting with RA and RB because the two registers which are coming, which are immediately outside the register file is RA and RB. So you just need to ensure that which one will go to RA and which one will go to RB. So that itself is sufficient. I actually do not know that why they have given the names of this RS and RT. Actually, in case of load, it should not be source. It is basically destination. Okay. So RS has no meaning here actually. It should be RD rather. That's why I told you, forget about these names. There are two registers, two fields. Okay.
Sir?
Obviously, as a designer, you must fix it. While you will design the circuit, you must connect it. Whether this one will be connected to RA or this one will be connected to RA, that you'll have to decide it. Bolo.
Sir, when you give us to design circuits, we are free to choose any one, right?
Yes, yes. You are free to choose anything.
No need to take according to MIPS. No.
No, 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 no. Actually, I have not given anything related to MIPS in the. I have just taken the concept of this one. So you will not find anything related to MIPS explicitly in the question paper. There is nothing. It's not there. But the concept you require. For example, how the instructions are designed, how many bits are required for each and every field. I just took the example of MIPS just to describe that. Because it's difficult to remember all these formats. Who will remember?
Also, the remaining registers which you didn't tell,
Also,
special registers.
yeah, so naming the registers are also difficult. That's why I told you, you do not need to remember the names of the registers. Okay. This is particularly needed when you write a program for MIPS 32. I'm not asking you to write a program for MIPS 32. Let me take your attendance today. Chandra Prasad, are you there?
Yes, sir.
Jitin?
Yes, sir. Done, sir.
Supriya? Supriya?
Present, sir.
Sudhanshu? Venkatasai? '19 batch. Roll number 1, Tarun.
Yes, sir, present.
Roll number 2, Aviram. Aviram, are you there? Nihant. Roll number 3.
Present, sir.
Roll number 4, Bharat Mishra.
Sir, he is having interview.
Hmm?
He is having interview from intern side.
Roll number 5, Akhil. Six, Pavan Kumar. Seven, Arpit.
Present, sir.
8, Anudeep, 9 Sujit, 10 Nitish,
Yes, sir. Present, sir.
11 Rohit, 12 Navneet,
12 present, sir.
13 Sukrit,
Yes, sir. Present,
14 14 Kusagra,
Present, sir. Present, sir.
15 Vijay Ketan, 16 Venkat, Avinash, 17 Jyoti, Jyoti Kiran Reddy, 18 Divyans, 19
Sir, he is also
He is
having
having
interview.
Atul Goel, 20 21 Avinav,
Present, sir.
22 Udit, Udit Reddy, 23 Sahiti,
Present, sir.
24 Niharika,
Present, sir.
Shravani, 25 Sri Sai, Janvi Sri Sai, 26 27 Bharat Kumar Reddy, 28
Present, sir.
29 Vidya, 30 Nandini, Sai Giri Nandini, 31 Ades, lot of students are not present. 32 Parvatala Teja, 33 Anand,
Present, sir.
Anandam, 34 Dheeraj, 35 Aviram,
Present, sir.
36 Vikas,
He
Present,
is
sir.
having interview.
No, sir, I just came back.
hmm?
Sir, I was in interview. It has been completed, so I am now in the class.
What is your roll number?
The 36.
हाँ ठीक है.
Okay.
37 Ramsi,
Present, sir. 37.
38
Present, sir.
38 yeah 38 Saket, 39 Nikhil Kumar, Bade Nikhil Kumar, 40 Anirudh,
Present, sir.
41 Ashwin Kumar,
Present, sir.
42 Santosh,
Present, sir.
43 Sindhu,
Present, sir.
44 Akshaya,
Present, sir.
45 Pranaya, 46 Abhijit,
Present, sir.
47 Pavan Kumar,
Present, sir.
48 Praveen Kumar, 49 Satvik, 50 Vimal, Monish, Sai Manoj, 51.
Manoj present, sir.
52, Vinith Babu.
Present, sir.
53,
Present, sir.
54, Jyoti Priya.
Present, sir.
55,
Present, sir.
yeah, 55.
Present, sir.
Vinay.
Present,
50
sir.
yes, 56, Dhruv.
Present, sir.
57, Kishore Kumar. 58, Vinayak. 59, Sujata.
Present, sir.
60, Rapeti Mohan. 61, Hers.
Present, sir.
62, Sangram.
Present, sir.
63, Jagdish.
Present, sir.
64, Yogesh.
Present, sir.
65, Prashant.
Present, sir.
Middle degree, Sai Krishna. 1,
Present, sir.
roll number 2, Dhiren. 3, Sarthak. 4, Harshavardhan.
Present, sir.
5, Deepthi. 6,
Present, sir.
7, Durga Prasad, Jogendra Durga Prasad.
Present, sir.
8, Agamay Yadav.
Present, sir.
Likhita. 9,
Present, sir.
Anuj. 10,
Sir.
Harshit.
Present, sir.
Sushant.
Present, sir.
Okay.
Sir, my roll number is CS25. Actually, I was in class, but I went to washroom in between, sir.
What
By
is your
the
roll
time-
number?
CS25.
Shavani. Okay.
Yes, sir. Thank you, sir.
Okay, done. So, anyone, any doubt on the topic that I have discussed so far today? I'll not advance the course again. Okay, so next week, whatever I will be discussing, that will not be part of the mid semester. I just want to know if you have any doubt up to the points, whatever I have discussed so far, just open it up. Let us discuss it.
So what kind of questions can we expect in mid-semester?
See, I already gave you clues in the last class. Probably I was talking about if I want to change, modify the hardware like this, if I want to do like this. So whatever questions I have asked in the mid semester, similar things I have already discussed in the class. That I can assure you. With a bit of what I will say, with a bit of intelligence required from your side. Okay, so what kind of modifications? It's primarily based on model. There are some straightforward questions also, but the percentage of straightforward question is maybe 30% questions are straightforward. Others are easy, but you'll have to think a bit. You do not get it directly from the book. Okay, but if you know the concept, you can easily answer it. That I can tell you. Like in one of the classes I was talking about, if I would like to bypass this, okay, if you remember, I think I was talking about this one, okay, from here to here directly multiplexer. So these sort of modifications you can think about, like one is here, another one is here I was talking about, okay. So similar things will be there. These are just examples. I cannot disclose it, obviously, but I believe that you will enjoy the question. Don't worry. If you have followed my class, if you have followed the lectures, I don't think you will find any difficulty in answering the questions. Obviously, this is an IIT standard question. I'll have to maintain some standard, and because you all came through JEE Advanced. Okay, so I need to test your IQ also.
Okay, sir.
Anything else? If you have no query, then I'll stop today. I do not want to advance in any part. Okay.
The lab class.
Lab we will be doing it today from 2 p.m. onwards, because I need to finish it by 5 sharp. I have a lecture from 5 o'clock. Okay, so even before 5 I would like to finish the lab. I think the 3-hour period. So today's lab will start at 2 p.m. Okay, today's lab will start at 2 p.m. All of you be ready.
So it is mandatory to attend.
Sorry?
Is it mandatory to attend?
No, because there will be no assignment given today. Okay, so only the evaluation for the initial 30 students. Okay, it is mandatory to attend for your attendance, obviously. Okay, otherwise it is up to you.
Sir?
Yes.
192002 is present, sir. He has mic problem.
192002.
Yes, message